Okay, so we continue with our rotational kinematics and dynamics, and we're going to start to move more into the dynamics part of this, although we really already did that when we talked about torque equals I alpha, but we'll be getting more into that, the torque and its relationship to angular acceleration, and looking at angular momentum today. So to start with today, we have a little exercise here that will hopefully tie together quite a few of the things that we talked about in the last lecture. Again, I mentioned you'll be learning more about torque in your lab next week, but you might want to pause the video at this point, read this problem and give it a try, and then restart the video and we'll see how you did. Okay, so hopefully you had a chance to work on this, and what we're going to do is see how to do this problem. It says, suppose a force of 50 newtons is applied tangentially to a playground merry-go-round, which is similar in behavior to a disk having I equal to 1/2 mr squared. It says if the merry-go-round has a mass of 100 kilograms and a radius of 2.5 meters, then what is the rate of angular acceleration that will occur? So again, starting, one important thing here to start with is that this force is being applied tangentially. And what that means, tangentially, means it's going to be perpendicular. So this is kind of an attempt at like a 3D sketch, okay? So if you viewed the overhead, if you made the overhead view of the merry-go-round, it has a radius of 2.5 meters, right? And the force is being applied like this. The force is being applied in such a way that the force is perpendicular to the radius. Okay, so this would be an overhead view that I'm showing right here. Okay, overhead view down here below would look something like that. Okay, so that's the important thing to, first of all, to make sure is understood. So to calculate the torque that force applies, remember the rule is that the torque is equal to FD sine theta, or basically the force times the moment arm. Remember, if we take the force and we extend a line to infinity both directions, we call that our line of action. And the shortest distance from the pivot location, which in this case is the center of the merry-go-round, the distance from that to the line of action, the shortest distance, which is going to be perpendicular, intersect the line of action perpendicularly, that is our moment arm. And so in this case, our theta is really 90 degrees, which means we're just taking the force times the radius, and we find out that the torque here is 125 newton meters of torque that's applied to this merry-go-round. Now that 125 newtons of torque is positive. Right? That is positive because this is the positive rotation direction. So this is positive rotation. Counterclockwise motion is the positive direction of rotation. So this is a positive torque is viewed from above. They tell us that the moment of inertia or rotational inertia of the merry-go-round is 1/2 mr squared. They told us the mass was 100 kilograms. Again, we know the radius of the merry-go-round is 2.5 meters. So when we do 1/2 mr squared, we get our moment of inertia or rotational inertia of 312.5 kilogram meters squared. You'll notice with this larger object, more several meters in size and 100 kilograms of mass, that we now are starting to get moments of inertia that are a little more larger numbers. Like we said, even small, regular, everyday sized objects like coffee cups and calculators and things like that, those things actually have very small rotational inertias typically. Okay, but then this is the rule that applies here. Torque equals I alpha. This is Newton's second law for rotating systems, if you remember us talking about that last class. And so we apply this law. Okay, this is the law. This is how things are working. And we say, well, then we can get the angular acceleration alpha if we take the torque and divide by I. And so we go ahead and do that. And if we're careful with our units, we end up with an answer of 0.4, and that would be in radians per second squared, because that's the standard unit for rotational acceleration or angular acceleration. Now, as we continue along, we've already looked at much of this. We've already talked about how the position x becomes our angular displacement theta, how our velocity becomes our angular velocity omega, how our acceleration becomes from A from A to alpha. We talked about how our mass, we can no longer talk about linear mass, we have to talk about rotational inertia, I. We've talked about torque equals I alpha for the second law of motion in a rotating system. So all this stuff on this chart down through there we've already talked about. Now it's interesting and important to note that this process of similar equations continues. Work done is force times distance, or the integral of force over some little integral of length that the force acts over while the object moves. And so that becomes work equals torque theta. So again, if we listed work as force times the displacement d while the force acts, then the work done in a rotating system is torque times theta, the angular displacement. So again, there's a direct analogy. If we're replacing force with torque, we replace distance or displacement with theta, and there would be our equation for work. Again, this is the calculus version that is listed there. Kinetic energy in a linear system, we said, hey, an object moving at speed v and having mass m has a kinetic energy of 1/2 mv squared. In place of m, we put I. In place of v, we put omega. And so in a rotating system, we have our kinetic energy for a rotating object of 1/2 I omega squared. So something like a rotating bicycle wheel, even if it's not moving across the room. What if it was, suppose you have a bicycle wheel up on a stand and you give it a big turn, it's spinning very quickly. I think you'll agree without much trouble if I have you, if you put your fingers into the spokes, you're going to agree that that spinning wheel has kinetic energy. It has energy of motion. Okay. Then we end up with our power equation. If you remember, power is the time rate at which work is being done, or the energy is being expended. And so that rule stays the same. Okay, that rule stays the same. It's work per time or energy per time. However, if you remember, we also talked about the power equation for like a car going up a hill. Sometimes you could just take the force times the velocity, the dot product of those. And so if we could also write, in place of force we use torque, in place of v we use omega, we could also write the power for a constant torque situation as torque times omega, where omega is the angular velocity the object's spinning with. Okay, the work kinetic energy theorem, we said if the work changes, if the kinetic energy changes, the net amount of work being done is equal to that change in kinetic energy. The same thing is going to be true in a rotating system. If the kinetic energy of a spinning object changes, then the net amount of work done on that spinning object can be expressed as work. So if you're on the ball here as a student in this class, you'll realize, okay, wait a minute, we already talked about a car moving down the road as having translational or kinetic energy because it's moving translationally down the road. And now we've just learned that a rotating object has kinetic energy. So what do we do with rolling objects? So like a bowling ball, when it rolls down the bowling lane, right, down the alley, it's actually not only is it moving in such a way that it's translating, right? So it's going to have some kinetic energy because of the fact that it's moving down the alley towards the pins, but it's also rotating, and so some of its energy is going to be stored in its rotation as well. Okay, so to find the total kinetic energy of an object, really what we have to do is we have to sum together those two types of kinetic energy. So in the past, when we were talking about a car going down the road, we know cars have wheels. But as we were talking about the car going down the road, we were simply saying, well, the kinetic energy is 1/2 mv squared, right? But really what's happening is the wheels have some rotation, and the engine has some rotation. So there's some energy stored in those wheels as well, and that's 1/2 I omega squared, where I is the rotational inertia of the wheels, and omega is the rate at which their angular velocity. So to get the total kinetic energy, we really need to add on both types of energy that are in that car. So really what we were modeling earlier was a car sliding along the road. So, we were talking about it as gripping the road and rolling and so forth, but really this equation just models the car, kind of like sliding along the road rather than anything rotating. Okay, and that's because we were modeling the car at the end of the day as like a point particle. So we were basically saying, there's my car of mass m, and it's moving at speed v, and therefore it has a kinetic energy of 1/2 mv squared. Okay, so now what we're doing is adding these together. And the nice thing is, if it's a rolling object, if it is an object that's round and it's rolling on the ground here, suppose it's rolling along, okay, there's going to be a nice direct correlation between the speed at which it's moving and the rate at which it's rotating. So in this case, I guess this wheel would be rotating this way if it was going in the forward direction, right? And the rule is that V equals R omega or omega equals V over R. So that's going to be true if this is the radius of this wheel that's rolling. These two relationships are going to be handy because they help us go back and forth between the omega and the V. Okay, a rigid object that's rolling and gripping the ground, there's a nice direct relationship, a link between these two, and that relationship is this. Okay. Okay, so looking at rolling motion is kind of a fascinating thing because it depends how you're viewing this. If we initially look at a spinning object, and let's suppose that the wheel is not moving. Okay, so let's suppose the center of the wheel is like on a rigid axle in the classroom. Then as this thing rotates, what we find is that the top of the wheel is going to be moving at some speed v in the positive direction, and then at the bottom of the wheel it's going to be moving at some speed v, same speed v, but in the negative direction. And so the bottom of the wheel is moving to the left, the top of the wheel is moving to the right. That's how it looks if we assume the center axle is our reference frame, our reference point, and we're viewing things with respect to that. However, if the wheel is rolling along down the road, then we kind of have to add that velocity into the situation. And when we do that, it turns out, because of this relationship between v and omega, that if the center of mass of the wheel here is moving at a speed we'll call VCOM, then the bottom of the wheel, if you look at this, if I add these two things together, right? So our speed v here is what we were saying is going to be the speed of the wheel down the road, right? So the center of mass now is moving to the right down the road, let's say at 56 miles per hour, right? But the bottom of the wheel now is gripping the road. And so the actual motion of the bottom of the wheel in that reference frame is 0. In other words, the bottom of the wheel we said was moving to the left at speed v compared to the center. And so when we have the center moving at speed v, then the bottom of the wheel is actually at rest. So down here at the bottom of the wheel we have 0 motion. The middle of the wheel, the center of mass, is moving, let's say, at highway speed, and then the top of the wheel would be moving at twice that speed. So if we're talking about highway speed of 100 or 56 miles per hour, then the top of the wheel is going to be moving at 112 miles per hour with respect to the road. So when we look at our reference point as being the gripping effect between the wheel and the road, right, using this as our 0 point instead of the center of the wheel over here, then what we find is that the top of the wheel is actually moving twice as fast as the center of the wheel, right? You could imagine if I think about if I draw a line here and we set an egg up here or something, a little while later that's going to have shifted over to here. Well, the center of mass may have moved a small amount, right? But the egg's going to have moved kind of twice as far because of the rotation of the wheel. So the top of the wheel is actually moving at twice the rate of the center of mass of the wheel. And this is one of the reasons on cars that they have fenders, right? One of the reasons on cars that we put like a covering over the wheel like that, so that any stones that might get stuck in the wheel here, instead of them shooting down the road or shooting back this way, they get captured, right? Because if I'm standing alongside the road, so if you're thinking about this right, if you're following along here, if I stand alongside the road and here comes a car, right? Here comes the car. All right, let me draw a little sketch here. So the car is now moving down the road, let's say at highway speed, 56 miles per hour. And again, I choose 56 because, as you know, that's the same thing as 25 meters per second. So that's a handy speed for us to think about. So here's the car, and the wheels are rolling. Well, if I'm standing here, right, alongside the road, the wheels are moving. The center of the wheels is connected to the car, and so the center of the wheels are moving at 56 miles per hour. But any stones or anything that's at the top, top of the wheel there, that might be lodged in the top of the wheels, is going to be moving with respect to the road at 112 miles per hour. Right? So if something comes shooting off the top of the wheel and I'm standing at rest on the ground, that piece of debris would be hitting me at 112 miles per hour. So it's important that we cover the tops of the wheels, especially in automobiles. It helps to prevent flying debris and so forth. Okay, now if we go down here in this diagram, this is an interesting diagram as well, because it's showing you that the edge of the wheel, okay, is moving, in a direction. We could look at this bottom. If this bottom is at rest, then the motion here, if we take a radial line out, is like this, and the velocity of the wheel is changing as we go around the wheel. In other words, it's moving fastest at the top of the wheel, and it's moving slower as you get down here to the bottom. And right down here at the bottom, of course, it would not be moving, as we talked about up in this diagram. So rolling motion is kind of interesting. It depends on the perspective, the place you're viewing it from. But typically what we do is we talk about the speed of the rolling object being the speed of the center of mass. That's usually what we do, right? If we had something rolling down the road at 56 miles per hour, the interpretation of that is that the center of the wheel is moving at that speed, right? We don't talk about, even though the speed at the top of the wheel is bigger than the bottom and so forth, we generally say whatever the axle is, that's kind of the speed of, we look at that speed as the speed of the object rolling down the road. Now, those of you that are really interested in your calculus and mathematics and so forth, if you ever get interested in this, you could watch, kind of trace out the edge of a wheel as it rolls, and what you'll find is that that edge, as the object rolls down the road, that dot on the edge of the wheel will trace out. So in other words, if you put a little glowing light on the edge of the wheel and it rolls down the road, what you'll get is traced out this curve that I'm kind of sketching out for you here, and that curve is called a cycloid. Okay, so for those of you that are interested in math, that's the mathematical shape, the cycloid, that matches that path traced out by a single point on the edge of a rolling wheel. So now, another interesting thing about rolling is that rolling cannot occur without some friction. Right? If there's no friction below our wheel is unable to grip the road. We've talked about this some as we looked at friction between the wheels of our car and the road surface. If the road is very icy, we just slide. Our wheels do not grip the road. And so for rolling to happen, we actually need some gripping, which means we actually need some friction. But the interesting thing is, you've probably heard the old story of the discovery of the wheel, how that was like one of the greatest discoveries of humankind, the discovery of the wheel. Oftentimes they talk about, the cavemen, chiseling out a circular shaped rock and realizing, wow, we can put an axle on this and it really makes moving things around easier. And that's exactly right, because if I zoom in, right, if we look at the bottom of a wheel and we kind of zoom in on that, right, so the wheel's gripping the road here, where I'm drawing the nice bold green dot. All right, and the rest of the wheel is kind of, pivoting around that point. Okay, and so if we zoom in on that bottom, so that our bottom of our wheel again is right here, and it's, let's suppose, an ideal rolling motion. Maybe there's like one point there that is gripping the road, and the friction. If this wheel's rolling to the right, then we need the friction acting to the left, resisting the motion, and that's what causes this, the pivoting action of the wheel. But if I really zoom in close, it looks like right to the left of that pivot point, the motion of the wheel is mostly upward, right? Let me change colors here. All right, so the pivoting of the wheel, if I look to the left of that pivot point, the motion's mostly upward. And if I look to the right of it, the motion's mostly downward, as far as the motion of the wheel. And so if I remember my formula for work, if the motion of the wheel is perpendicular to the direction of the force, so we know our friction here, we know our friction is acting along the left and right direction here, right? That's what's causing the rolling motion. But our motion is pretty much perpendicular to that force direction. So it turns out that in rolling motion, friction does not do work. It does not remove energy from the rolling object. And that's what makes rolling motion and the wheel such an interesting and important discovery, because we need friction to cause rolling, but because of our work equation and because this angle is so close to 90 degrees, cosine of 90 is 0, And so since the force and the displacement or the motion is perpendicular, we end up with virtually no work being done by the friction in rolling. If it's ideal rolling, no loss of energy, right? We roll the bowling ball down the bowling alley, and we have friction to roll the ball, but the ball, ignoring any real loss of energy, would just keep rolling. In an ideal world, if that was just a single point at the bottom of the bowling ball that contacted the plane of the bowling alley, then the ball wouldn't ever really stop because there's no heat or there's no friction taking energy away and turning it into heat. Okay, now in real rolling motion, if we think about a car wheel, for example, right? In a car wheel, for example, the bottom of the wheel in a car is not perfectly not touching at one point. The bottom of your wheel of your car or any vehicle that you ride in, if you look at the vehicle, you'll notice the bottom of the wheel is a little bit flattened because of the weight of the vehicle. And so really, it isn't just one point here where the friction acts. The friction acts over a distance like this. And by the time you get over here, there's going to be a little bit of a tilt and a little bit of a tilt in the motions, and the angle's not going to be quite 90. And you're going to start to dissipate some energy at these bottom points of the wheel here where it's going to rub the road. And of course that wears your tread down, it wears your tire out, and it also causes some energy to dissipate. So in real rolling, like in the bottom of a car wheel, we do end up dissipating some energy and we do end up wearing out our treads, but ideally, in ideal rolling, no loss of energy. Okay, so let's start to get a little more practical here, and let's start to look at some numbers and start to see how we might apply this new information for problem solving. So what we here see at the top of the slide, as noted, is that conservation of mechanical energy is still going to work. All the rules we had before, as we've talked about, they don't go away just because we've now introduced rolling motion. It's just the rolling effects have to be incorporated into our rules. And so here's a good example of that. It says we have a 300 kilogram spherical boulder with a radius of 1.5 meters and it's at rest. If the boulder is pushed until it is rolling along with a speed of 9.5 meters per second, then how much work was done by the applied push? So the assumption here is that the push is kind of happening along the direction of motion. Okay, I want to make that part clear. So somebody's kind of pushing, let's say, on the sides of the axle or something like that to push this boulder straight forward, if you will. Okay, and it's starting from rest, and it gets up to 9.5 meters per second. Now, what's moving at 9.5 meters per second? Well, again, the assumption is always the center of mass is what we're talking about. So the center of this boulder is moving at 9.5 meters per second at the end of our problem. So we have our initial velocity and our final velocity, or in other words, our initial speed and final speed. We just happen to choose this rolling from left to right. So when we go to solve out for the kinetic energy of this particular boulder, we know we just learned that we have to consider the moment of inertia or rotational inertia of this solid spherical rock. And if it's a solid sphere, that's a solid ball, and we learned before that the moment of inertia or rotational inertia is 2/5 mr squared. We talked about that last class, and it was also in that chart of a lot of common rotational inertias. So if we take that in this case and we say, well, let's calculate what that would be, we would have 2/5 times the mass of the object times its radius squared, and we find out that this boulder has a rotational inertia of about 270 kilogram meters squared. Okay? Now, it's starting from rest, and so originally it doesn't have any rotational velocity. But then after it starts to roll, we know it gets moving down the road here. The center of mass velocity ends up being 9.5 meters per second, and so it's definitely turning if it's rolling, okay? And we're told that it does roll. So in this particular case, how do I get the omega final? Well, again, remember that omega is the same thing as v over r, and in this case, the center of mass velocity is our velocity, and so we just take the radius with respect to that, and what we end up with is our 9.5 meters per second divided by 1.5 meters radius gives us our omega. Okay, so in other words, omega equals v over r. This is an important relationship that you'll see coming up over and over again throughout the rest of today's lecture. So v, 9.5 meters per second, the velocity of the center of mass divided by the radius gives me the angular velocity. So now we've got an original angular velocity of 0, a final angular velocity of 6.33 radians per second. Okay, so again, this relationship right here that I wrote in yellow and put into your notes up there, and I've rewritten right here, that's a really important relationship for connecting the motion of the center of mass of the rolling object back to its angular velocity. So now, as we go to calculate the kinetic energy at the beginning of the problem and the kinetic energy at the end of the problem, the kinetic energy equation is 1/2 mv squared plus 1/2 I omega squared. So using our initial values for velocity and omega, it was originally not moving sideways, and we also know it had an original angular velocity of 0, and so obviously not moving at all, not rolling, not sliding along the road. The initial kinetic energy in the system was 0. The final kinetic energy will be 1/2 mv final squared plus 1/2 I omega squared. 1/2 times the mass of the boulder times its radius, or I'm sorry, its final speed squared gives me the final translational kinetic energy, right? That's how much energy is kinetic energy of it translating or moving side to side down the road. But I also have to add on 1/2 I omega squared. So this was the 270 kilogram meters squared of rotational inertia. We found out that was about 6.3 radians per second that the wheel was turning at if it's moving down the road at 9.5 meters per second. And so we have to add that on. And when we add that on, we notice that the answer gets quite dramatically different. Okay, so we have some rotational kinetic energy as well. And when we add them together, we get almost 19,000 joules of kinetic energy. Now, what was just the translational kinetic energy? What if I'd forgotten? What if I was a student who wasn't paying attention and I had forgotten this? Kind of like what we were doing earlier in the semester. If I just calculate the translational kinetic energy here, that would be, let's see, 9.5 squared times 300, and then divide that by 2. I'm getting an answer here for the translational energy of only about 13,500 and we'll say 38 joules. So ignoring the rotational part of this problem, I'd only think I had 13,538 joules of kinetic energy at the end. But that is not correct, because I do have to add in this amount of rotational kinetic energy, and when I do that, I get the correct answer here of almost 19,000 joules. So again, rolling objects are both translating and rotating, and we have to account for the kinetic energy of both. So in that last slide, obviously using the work kinetic energy theorem, the change in kinetic energy was about 19,000 joules roughly, and so that was the net amount of work that our force did at getting it moving. Let's switch to looking at objects rolling down a hill. Okay, obviously there's various shaped circular objects that could roll down a hill of height h. Let's suppose that every one of these objects is going to have the same mass and the same radius. And that can happen. We actually in the physics lab have a metal hoop, a metal ring basically, that has about the same mass as a solid wooden disc that has the same radius. So if this was made of wood, you may find that it has the same mass and the same radius as the ring made of metal. So what we're going to do here is we're going to actually just assume that all these objects here have the same mass and the same radius, just to keep things simple for right now, okay? So we're going to start these objects, think about starting them from the top of this hill at some height h, okay? If they all have the same mass and they all start from rest, then obviously all the energy is initially gravitational energy. If we're looking at it from an energy standpoint, all the energy is initially gravitational energy in this system. Now, if we call this the zero height down here, when the object rolls down the hill, obviously down here it's going to have zero rotational. Well, actually, I guess I should call the zero height at the level of the center of. Well, I don't want to confuse you, but some of you might be looking at this going, well, don't you measure the height of the object from the center of mass? But keep in mind, then that would just whatever that height is up here, we add that on to the height of the hill. So really the diagram's a little off. This should be the height h to the bottom of the hoop there, right, like that. Okay, and so if that's the height h from here to here, then this is the height, this is the same height h. Okay, I hope I didn't confuse you with that, but I just was looking at my diagram and didn't want anybody to get confused from that. So basically the wheel's starting from a height h above our zero height. Okay, so we'll measure from the bottom of the wheel essentially and pretend that that's matching up with the bottom of the wheel there. So if this is 0, then at the end of the problem, there's no gravitational energy. The motion is all going to be kinetic, right? It's going to be moving at some speed v at the bottom of the hill. All right, and so the final kinetic energy should be equal to the gravitational energy at the start of the problem. So if we're looking at this and you're thinking about it right, you're saying, well, geez, every object is the same radius and every object is the same mass. So every object's going to start with the same gravitational energy at the beginning, and therefore it has to end up with the same kinetic energy at the end. However, that's true, but the kinetic energy, remember, has two categories. Okay, the kinetic energy is going to be a sum of its translational kinetic energy plus its rotational kinetic energy. And the way those break down, the way how much percentage is in each one depends on the shape, as you're going to see here. Okay, so let's go ahead and what we're doing here is really like we want to race these objects down the hill. If I just let them roll under the influence of gravity and they start from rest at the top of a hill of height h, they all start with the same gravitational energy, and we're just going to see how fast they end up moving here at the bottom. We're going to do a calculation for how fast these objects end up moving, we have different shapes. So we're going to do it, for example, for maybe a hoop and a disc. Let's just race a hoop and a disc and see which one would get to the bottom of the hill faster. So we're going to calculate it first, okay? Okay, so here's the question. Which would you expect to roll down an inclined plane faster? A hoop with I equal to mr squared, right? A rotational inertia of mr squared, or a disk, which has a moment of inertia or rotational inertia of 1/2 mr squared. So if you remember what rotational inertia is describing, it's describing how difficult it is to make something rotate. So a larger rotational inertia would mean it's more difficult to rotate. Okay, and so let's think that through, and you might instinctively have a guess now, but let's do the math and see if we can prove what we suspect to be the case, because it's gravity working on both objects. So as we look at this for the hoop, okay, if we do the calculation for the hoop has an I value, a rotational inertia mr squared. We know this omega for rolling object, the rate of rotation omega is just the rate of the velocity of the center of mass divided by the radius of the rolling object, right? Omega is v over r. And we know the kinetic energy that the hoop would have at the bottom of the hill would be 1/2 mv squared plus 1/2 I omega squared. So we want to solve for v though. And so what we'd like to do is try to get this I and this omega here in some form that is helpful to us. And so if I plug in for I know the I value here for the hoop is mr squared. I know omega is v over r, right? And then I'm going to square that as well. So plugging in for I and omega here, right? I and omega into the equation, notice that I end up with 1/2 mr squared times v over r squared. Well, this r in the bottom, when it gets squared, is going to cancel with the r squared here. And we're going to end up with our 1/2 mv squared from our translational kinetic energy plus 1/2 times m times v squared. Another 1/2 mv squared for our rotational kinetic energy. So it turns out in a hoop, when it rolls, half of its energy is rotational, the other half, half of its energy is translational, half of its energy is rotational as far as its kinetic energy. And so when we add those up, we get mv squared. 1/2 mv squared plus mv squared, 1/2 mv squared plus 1/2 mv squared is mv squared. Okay? But remember, all the energy started as the gravitational energy initially, which was mgh, right? mg times the height of the object off the zero level. So when we set those equal, we end up with the equation mgh, the original gravitational energy, right? That's what this is, right? Has to be equal to the final kinetic energy, which we just calculated as mv squared. So when we solve that out, we find out that the hoop at the bottom of the hill is moving at a speed v equal to the square root of gh, right? The mass of the hoop cancels. Notice the radius canceled up here. And guess what? Any size hoop any radius hoop with any mass will roll at a speed square root of GH at the bottom of the hill. That's what that means. It's the radius of the wheel and the mass of the wheel are independent. We get an answer, any hoop released from the top of a hill of height h, right? Any hoop released from the top of a hill at height h will end up at the bottom of the hill moving at a speed square root of GH. Okay? Now, if we look at the disk, we do a similar sort of calculation, except with the disk, the rotational inertia is 1/2 mr squared, but omega is still v over r because it's still a nice circular object rolling along. So when we go to calculate our total kinetic energy, we plug in for I, which in this case is 1/2 mr squared. We plug in for omega, which is still v over r, right? And so when we do our calculation here, notice what happens. Again, the r on the bottom here that's getting squared cancels with the r squared there, but we have a 1/2 times a 1/2 here. And so now, adding on the translational kinetic energy, 1/2 mv squared, we now have the rotational kinetic energy, which is only 1/4 mv squared. When we add those together, we get 3/4 mv squared. Okay? So in other words, in the rotating disk, about 2/3 of its energy is translational, and only 1/3 of its energy is rotational. Okay? But it still has the same total kinetic energy at the end. It doesn't look that way because we get a different formula here, but keep in mind that's just describing it in relation to the mass and the speed of the center of mass. Okay, so now we set that total kinetic energy for the disk at the bottom of the hill, and we set that equal to the original gravitational energy. Once again, solving for the kinetic energy, I've used a KE there instead of just a K. That should just be a K there because your book just uses K for kinetic energy. Some books use KE, and I go back and forth between books, and so sorry about that. That E shouldn't be there. But anyway, we get this equation. We find out that, okay, the original gravitational energy that the disk had at the top of the hill, that's equal to its kinetic energy at the bottom, 3/4 mv squared. The m cancels. And now I find out that for any disk of any radius or mass m, if it's released from the top of a hill of height h from rest, by the time it gets to the bottom of the hill, it will be moving at a speed of square root of 4/3 GH. And notice that that is a bigger number. That is a larger number. Square root of 4/3 GH is a bigger number than a square root of GH. So the disk is going to end up moving faster, side to side. It's moving faster down the road at the bottom of the hill than the hoop is. The disk will beat the hoop down the hill. Okay? It will get there faster. It has less rotational inertia, right? 1/2 as much. And it's going to get down the hill easier, being under the influence of only gravity. And when it gets to the bottom of the hill, it's going to be moving faster. It's going to win the race. If we release the hoop and the disk from the top of the hill at the same time, the disk will end up at the bottom of the hill first, and it will end up moving faster at the bottom of the hill. Yet, they both will still manage to have the same KE total at the bottom of the hill. Okay? They both will have the same total amount of kinetic energy at the bottom of the hill because kinetic energy is conserved. The gravitational energy here is being converted to kinetic energy. The gravitational energy here is being converted to kinetic energy. The same thing for both. So they both end up with the same final kinetic energy. It's just that more of the, a larger percentage, about 66% of the energy, kinetic energy is in translational motion, side to side. Only about 50% of the energy of the hoop is in its side-to-side motion. It's got extra stored in the rotation. But when you add up the rotation and the translation together, both objects will have the same kinetic energy. So they will both be just as hard to stop. Tying this in with our question earlier, when we pushed the boulder to get it up to a certain speed, right? We used a force, got it up to a certain speed, and we said, okay, how much work did that take? We looked at the change in the kinetic energy. And we said, well, if the change in kinetic energy was 19,000 joules, that means that was the work done. So both of these objects now have the same kinetic energy. If I want to bring them to rest, using some kind of braking mechanism, for example, right? I still have to do the same amount of work to stop the hoop as I do the disk. In other words, they're both going to be just as hard to stop, right? This one's going faster, the disk is going faster, but the hoop has more rotational sluggishness, and so overall it's just as hard to stop the hoop as it is the disk, even though the disk's going faster. Okay, and that's because they both have the same total kinetic energy. I hope that makes sense. let me see if I can find a little video clip of a disc beating a hoop down a ramp. Okay, so here we see a video of someone releasing a disc and a hoop that have the same mass and radius. They release them from the top of an inclined plane at the same time, and they race down the hill, and you can see the disc wins the race. So the next thing we're going to talk about is angular momentum, and I think we'll hold off and save that for our next lecture. So have a great weekend, everybody.